This video tutorial focuses on analyzing test questions on the second law of thermodynamics. What are the three laws of thermodynamics? First, we have the zeroth law, which states that two systems individually in thermal equilibrium with the third system are in thermal equilibrium with each other. Okay? So two systems are in thermal equilibrium. There is no net flow of heat between the two systems when they are brought into thermal contact. So we can illustrate it. For example, if system A is in thermal contact with a third system, system C, and that system C is also in thermal contact with system B, then it follows that the two systems A and B are also in thermal contact. Then we also have the first law, also known as the law of energy conservation, which states that the change in internal energy of a system is equal to the amount of heat that it absorbs or liberates, and that the amount of work it does on its environment. Okay? Mathematically, it can be expressed in this equation, where delta U represents the change in internal energy of the system, and that is equal to the amount of heat that it absorbs or liberates. Big Q stands for the amount of heat that is absorbed by the system or that is liberated. When it's absorbed, we treat Q as positive. When heat is liberated, we treat Q as negative. And the amount of work that the system does, all right, which is treated as positive when the work is done by the system on its environment, and treated negatively when work is done on the system, meaning work done by the environment on the system. And of course, our emphasis for this tutorial, which is the second law, okay, it comes in two statements. First, we have the heat flow statement, which simply says that the thermal energy flows spontaneously from a substance at a higher temperature to a substance at a lower temperature, and does not flow spontaneously in the reverse direction. When you say spontaneously, it simply means naturally. Okay? Uh, it is possible to reverse this natural flow, but there has to be a work done from the outside, meaning an outside agent will be doing the work on the system for it to be able to reverse the direction of the flow of heat. Now, we also have the entropy statement, where entropy refers to the degree of randomness of the particles that constitute a given system. So, the second law of thermodynamics expressed in entropy statement simply says that the total entropy of the universe does not change when a reversible process occurs, and it increases when an irreversible process occurs. Let us now answer question number 1. Which of the following thermodynamic processes or events is or are considered reversible? Okay, we're looking for one or more answers. Letter A, the two isotherms from the word isothermal, and the two adiabats from the word adiabatics in a Carnot cycle. Letter B. 1 kilogram of ice at 0 degrees Celsius is melted and converted to water at 0 degrees Celsius. Letter C. 1 kilogram of water at 0 degrees Celsius is heated to 100 degrees Celsius. And letter D. 25 grams of the metal gallium melts in your hand. So which of these four events or processes is or are considered reversible? Okay. Our answers are, all right, only options A and B are considered reversible, okay, where the change in entropy of the whole universe that's represented as delta S, okay, change in entropy is labeled as delta S. And in any reversible process, such as A and B, are considered reversible. Okay, so for any reversible process, the total entropy of the universe remains constant. In other words, there will be no change. That's why delta S of the universe is said to be equal to 0. Okay, so once again, we define what a reversible process is. It is one in which both the system and its environment can be returned to exactly the states that they were in before the process occurred. So we are saying that uh, in a typical Carnot engine, all right, uh, there are two processes involved in that. Um, the isothermal process as well as the adiabatic processes. Okay, so you can go to the details of the discussion of a Carnot engine, heat engine. You will find out that for one complete cycle, it involves two isothermal and two adiabatic processes. So in each of these processes, all right, the whole cycle illustrates an example of a reversible process where we say that the uh, change in entropy, okay, both for the system and its environment, okay, is such that the sum of the entropy change of the system and the entropy change of its environment is what we call the change in entropy of the universe, and that has to stay equal to 0, meaning no change. Okay, so uh, letter B, when ice melts without changing its freezing temperature, which is 0 degrees Celsius, that also illustrates reversible process because it is possible to freeze back, all right, the melted ice as if nothing happens. The two processes, melting and freezing, are reversible. So we illustrate that uh, in our examples. For more examples of the two processes, a firecracker that explodes, okay, is an example of irreversible process, while, as mentioned already, melting of ice at its freezing or melting temperature is an example of reversible process. Question number 2. According to the second law of thermodynamics, for any process that may occur within an isolated system, which one of the choices below applies? Okay, so we have three processes. Process number 1, the entropy remains constant. All right. Number 2, the entropy increases. Number 3, entropy decreases. Right. Our choices are, for letter A, it's only number 1, statement number 1 is or does apply. Okay. Letter B, only choice number 2 will apply. Letter C, both case statements 1 and 2 will apply. Or is it letter D, both statements 1 and 3 will apply? All right. So here's an example, a picture that shows an example of a process. Okay, demolishing a building like the one shown. Okay, illustrates an example of a process or an event happening. All right. So what is the correct answer? A, B, C, or D? The answer is, let's first consider the concept being applied here. It is the second law of thermodynamics, which states that the total entropy of the universe does not change when a reversible process occurs. Okay, we stated this earlier, that the change in entropy of the universe remains constant, meaning there is no change. Delta S is equal to 0 joule per Kelvin. That's normally the unit for uh, change in entropy. Okay, that is true if the process is reversible. Okay, the delta S equals 0, meaning the entropy of the universe stays constant. So that makes statement number 1 acceptable. And increases when an irreversible process occurs. Okay? It can be stated that the delta S, or the change in entropy of the universe, is greater than 0. Alright, so that means statements 1 and statements 2 are both correct. So which option, okay, describes that? Of course, the correct answer is letter C. It's not possible for the delta S of the whole universe to decrease. Okay, that's not possible. So, in as much as most processes in the whole universe are considered irreversible, okay, there are very limited number of processes that we can think of which are, strictly speaking, reversible. Okay, most most processes, if not all, are considered irreversible. So that means uh, in the whole world, you are heading towards a greater degree of randomness or degree of entropy, okay, which sometimes is also stated as uh, order is heading towards disorder. Question number 3. Suppose you wish to improve the efficiency of a Carnot engine. Which of the following methods will result to the highest efficiency? A. Lower the TC, or the temperature at the cold reservoir, by a factor of 4. B. Raise the temperature in the hot reservoir, or TH, by a factor of 4. Letter C. Cut TC in half and double TH. Letter D. All of this. All right, so we use the formula for the Carnot efficiency. That is, efficiency is equal to 1 minus the ratio of the cold temperature in Kelvin divided by the hot temperature also in Kelvin. Okay, so let's look at our calculations for the efficiency if we are going to follow each of the methods A, B, and C. All right, for letter A, if we lower the TC by a factor of 4, that means if the initial value of TC is 200 Kelvin, while the hot temperature is 600 Kelvin, so 200, when you lower it by a factor of 4, that simply means it becomes 50 Kelvin. So using the formula, E is equal to 1 minus 50 divided by 600 Kelvin, the result is an efficiency of 0.92 or 92%. For letter B, raising the TH by a factor of 4, okay, meaning if the initial TH is 600 Kelvin, so multiplying it by 4, we are going to have a TH value of 2400 Kelvin. So again, using the formula for E, 1 minus 200 Kelvin divided by 2400 Kelvin will also result to the same efficiency equal to 0.92 or 92%. And for the third method, cutting the TC in half and at the same time doubling the TH will also produce, okay, the same efficiency, because when you say cutting the TC in half, for our original TC that is 200 Kelvin, now it becomes 100 Kelvin. Okay, now doubling the TH initially is 600 Kelvin, so we'll make it 1200, and solving for efficiency, 1 minus 100 divided by 1200 will give us the same value for efficiency, 0.92. Hence, our answer for this question is letter D. All of them are methods that will result to the same value of efficiency. We call it Carnot efficiency. May I also add that in interpreting this formula for efficiency, what do you think will be the highest efficiency possible, theoretically speaking? All right. That will happen if the value of TC, okay, and TH is such that the ratio is equal to 0. Okay? If the ratio of TC over TH is equal to 0, then the efficiency becomes 1 minus 0 or 1, meaning 100%. But that would require lowering the cold temperature or the temperature in the cold reservoir to 0, meaning 0 Kelvin, which in reality is not yet possible. So, it is quite impossible to have a machine or a heat engine whose efficiency is 100% because of that limitation. Theoretically, it's not yet possible. All right. Now, when is or under what circumstance is the efficiency equal to 0? That will happen if the ratio TC over TH is equal to 1. And what does that mean? Okay, the ratio TC over TH will become 1 if TC is exactly equal to TH. That makes efficiency equal to 1 minus 1. All right? So, efficiency will be 0. Now, the best way that is, shall we say, practical is to, just like what was illustrated in our methods given in the choices A, B, and C, the best way to increase or maximize the efficiency of any heat engine is to uh, come up with a difference in TC and TH as great as possible. Okay, making the difference between the two, meaning lower the temperature, okay, as much as possible, and then increase the TH as much as possible. How are these being applied nowadays? Okay, uh, you must be familiar with some ways of making the efficiency of, let's say, car or vehicles. Okay, vehicles that make use of gasoline engine or probably a diesel engine. Okay, you must have heard about using some additives that can increase or that can lower the temperature of uh, the what do you call this? The water that is placed inside the radiator. Okay, the radiator is part of the cooling system of any automobile. So the best so far that they have achieved is to come up with such kind of uh, mixture that can lower, okay, the temperature, but to as much as very low, okay, uh, but at least such development, okay, has indeed make the efficiency of most automobiles very high. And also, research is ongoing to come up with a kind of engine whose material will not melt if the temperature of the hot reservoir is increased. Okay, uh, TH increasing TH would affect, okay, the durability and the ability of the material that the engine is made of, because there is a possibility at a very high temperature the material will possibly melt. So that's not a good idea. Okay. Research is now ongoing to look at the possibility of using an engine, okay, a heat engine that is made of ceramics, but that has yet to be proven if indeed materials made of ceramics can increase, okay, the the melting point of the material so as to withstand a very high temperature in the hot reservoir. Question number 4. How does a refrigerator operate? Right? We know that one example of the application of uh, the second law of thermodynamics is, okay, the operation or the working of an electric refrigerator. So you're given uh, some statements here that describe the sequence or the steps, okay, that explains the operation of a refrigerator. So your task is to arrange them so as to come up with a logical paragraph, okay? Logical paragraph that explains how a refrigerator operates. So this is the schematic diagram of a refrigerator, all right? Uh, Maybe you are already familiar with such terms like the compressor, right? Compressor that is usually create the noise, okay, when your refrigerator is uh, or when you connect the plug of your refrigerator to the voltage supply, okay, which makes the compressor start to work. All right, and outside the refrigerator or at the back of the refrigerator, okay, you will see some pipes, small pipes. Okay, these are, according to this diagram, refers to the condenser, right? The condenser. Okay, somewhere inside the refrigerator, but it's not really that visible if you're going to open your ref, all right? Underneath or beneath those walls inside, okay, you will find there what we call an evaporator, all right? Evaporator from the word evaporate, condenser from the word condenser, okay? So how do you arrange these statements, okay, which are labeled here as 1, 2, 3, and 4? I leave it to you to go through, read, no, each step. Right now, they are not arranged in sequential order. You are to arrange them so that you will come up with a logical paragraph that will explain the operation of this refrigerator. Okay. Basically, what is a refrigerator? Well, an electric refrigerator is actually a machine. All right. An example of a heat engine. Okay. What is its basic purpose? Its basic purpose, of course, is to extract heat from inside the refrigerator, all right, so as to keep the food inside the refrigerator as cold as possible. But as we all know, in an ordinary cooling box, if you want to maintain the temperature, the low temperature of your food or your drinks in an ordinary ice box, okay, you have to make sure that the ice or the chunk of ice that you place inside together with your soda or your soft drinks, you know, as time passes, we know that uh, the chunk of ice will eventually melt and obviously will become cold, all right, because the heat from the outside, meaning the environment, okay, spontaneously will flow into the inside of your ice box. So that causes the ice to melt and therefore make the temperature inside approach room temperature. But if you want something that can keep the temperature of the food, okay, people have invented this kind of technology, all right? A machine that can somewhat reduce or reverse, okay, the direction of the flow of heat transfer. Okay, instead of the heat moving from a hotter body to a cooler body, meaning from the outside to the inside of the refrigerator reverses this direction. But this is only made possible because of the presence of what we call a compressor. All right. So by going through these steps, I'm sure you'll be able to get the idea, okay, as to what's really the correct sequence. So I'm giving you a few seconds to do that before I reveal the answer. All right. So your 30 seconds is up. So I will now reveal the correct sequence. Which among those choices, I'm sure you were able to come up with your own logical sequence of these steps. All right. Is it letter A, letter B, letter C, or letter D? Now, if your answer is letter B, all right, that is the correct sequence. Meaning, we start with the fourth statement here, which says the compressor compresses the freon or the refrigerant. Freon is the refrigerant into a pressure of several atmospheres, right? And then the gas is cooled to near room temperature, which then condenses into liquid of high pressure. So this part of the process is what the condenser is doing. This is outside the refrigerator. Okay. After that, then we proceed to number 3. The liquid evaporates due to its low pressure, and then the heat is absorbed from the contents of the refrigerator. This now pertains to the evaporator inside the ref. Okay, where the food, okay, the food will be the heat coming from the food, okay, will be absorbed by the what do you call this, the refrigerant. Okay, and lastly, the last step, the gas produced that has already absorbed it goes back to the compressor, and then the cycle will just repeat itself. So that is the correct sequence. Okay, that explains the operation of an electric refrigerator. Question number 5. A Carnot engine takes 2000 joules of heat from a reservoir at 500 Kelvin, does some work, and discards some heat to a reservoir at 350 Kelvin. Question letter A, how much work does it do? Letter B, how much heat is discarded? And letter C, what is the efficiency of this engine? So you're given the following choices. Okay. Uh, the amount of work done, all right. The amount of heat, or big Q, absorbed or discarded, and of course the efficiency, okay, are all given for letter A, B, C, and D choices. So which among these options, okay, gives the correct values for the work done, for the heat Q, and for the efficiency, right? So our solution, first, let's identify the data. When you say QH, this pertains to the amount of input heat or heat input, okay, that is provided by the hot reservoir of the engine, right? And then the temperature at the hot reservoir or hot part, okay, whatever it's called, is 500 Kelvin, while the cold reservoir is 350 Kelvin. So, uh, we will first answer letter B, question letter B, how much heat is discarded, okay? Because we can directly determine that using this formula, QC is equal to the product of QH multiplied by the ratio of TC over TH. And substituting, okay, to find QC, we have 2000 joules as the amount of the input heat, okay, multiplied by the cold temperature 350 Kelvin over the hot temperature 500 Kelvin. So we get the value for QC equal to 1400 joules. But according to the problem, letter B question, the term used is discarded. How much heat is discarded? So this value for QC should be indicated with a negative sign. All right? Following our sign convention that we mentioned earlier on in our discussion, okay, when the value or when the amount of heat is being discarded or liberated, okay, we have to make that value of Q as negative. Now that we know the value of QC, we can proceed determining the work done, okay, W, which is simply the sum of QH plus QC, where QH is known to be 2000 joules, and then we add that value of QC already emphasizing that it is negative. Okay, so 2000 plus negative 1400 joules will give us 600 joules, of course. All right, since it is the system that is doing the work, therefore it is considered a positive work. Okay, and finally, determining the efficiency. Again, we make use of Carnot efficiency formula, which is 1 minus Tc over Th, where the Tc is given 350 Kelvin divided by the Th, which is 500 Kelvin, and our value for efficiency for this Carnot engine is only 0.30 or 30%. So which among the options in the table is the correct answer? Cool. So the work done has to be 600 joules. There it is. And the value for Q must be negative 1400. And the efficiency is 30. And therefore, our answer must be letter C. Question number 6. Two equal amounts of water are mixed together in an insulated container. The initial temperatures of the water are different, but the mixture reaches a uniform temperature. Which descriptions in the table about the energy and the entropy of the system is correct? Alright, so for letter A, the energy is constant but the entropy increases. Letter B, energy increases, entropy remains constant. Letter C, energy decreases while the entropy increases. And letter D, both energy and entropy remain constant. What do you think is the best answer? Alright, so the answer is uh, the energy of the system remains constant. Okay, and this is supported by the first law of thermodynamics, that the amount of energy before and after any given process or event must always be kept constant. Okay, but the entropy increases since we consider the process described in the question to be irreversible. Okay, that now falls under the second law. Okay, if the process is irreversible, uh, the amount of entropy, okay, will increase. This is referring to the total amount of the change in entropy of the system plus that of the environment. So when you combine the delta S entropy, delta S of the system and the delta S of the environment, you are talking about uh, the change in entropy of the whole universe. which we earlier stated that if the process is irreversible, uh, such delta S, okay, is always um, or is always greater than zero, meaning there's always an increase. Okay, there's always an increase in the entropy. It's only when the process is reversible where the entropy of the whole universe will stay constant. But that is very rare because most of processes in the world are irreversible. Therefore, okay, our answer is letter A. Energy is constant and entropy increases. Question number 7. An event happens somewhere in the universe, and as a result, the entropy of an object changes by negative 5 joules per Kelvin. Which one or more of the following is a possible value for entropy change for the rest of the universe? Is it letter A, negative 5 joules per Kelvin? Letter B, 0 joule per Kelvin? Letter C, positive 5 joules per Kelvin? Or letter D, positive 10 joules per Kelvin? So, our answer is explained this way. If the process is reversible, okay, then the delta S of the environment would be positive 5 joules per Kelvin, inasmuch as the delta S of the system is negative 5 joules per Kelvin. So if the process is reversible, okay, that would mean they will have the same magnitude of delta S. All right. Notice that when you add the two, all right, negative 5 joules per Kelvin plus positive 5 joules per Kelvin, that will give us a delta S of 0 joule per Kelvin, and that the sum actually represents the change in entropy of the universe. All right, so we take note that the positive joule per Kelvin is an acceptable answer, as well as the 0 joule per Kelvin, which refers to the delta S of the universe. Now, if the process is irreversible, all right, if it is irreversible, then we must have the value for the delta S of the environment, okay, to be positive 10 joules per Kelvin, all right, while where if you're going to add positive 10 joules per Kelvin to the amount of delta S of the system, okay, that is positive 10 plus negative 5, will give you a total of positive 5. And that would mean positive 5 joule per Kelvin will be the total delta S, okay, also the delta S of the universe. Okay, so it shows that among the given choices, letter B, C, D looks like they are acceptable. We cannot accept letter A because that is already the given delta S for the system. All right, and the question is asking only which one or more of this is a possible value for the entropy change for the rest of the universe. In other words, uh, not including the system, but referring only to either the environment, okay, or the rest of the universe. So only B, C, and D are considered correct answers. We do not consider letter A. Question number 8 is a problem-solving question. A Carnot engine whose high temperature reservoir is at 620 Kelvin, takes in 550 joules of heat at this temperature in each cycle and gives up 335 joules to the low temperature reservoir. Question letter A. How much mechanical work does the engine perform during each cycle? Letter B. What is the temperature of the low temperature reservoir? And letter C. What is the thermal efficiency of the cycle? So we have here a simple illustration or schematic diagram of a Carnot engine. Alright, we have here the hot reservoir whose temperature of course is given. Alright, and you will notice that when the engine functions or works, alright, part of that heat input, okay, is used to do work, okay, to do work or to convert heat into useful mechanical energy. And that energy that is obtained, okay, is what makes the car run. So we call that the amount of work done, okay, or the amount of mechanical energy that is produced by any heat engine such as a gasoline engine. But there will always be, okay, certain amount of the input energy that cannot be utilized or turned into useful mechanical energy. So this ends up in the cold reservoir. So we use the term, this amount of heat is being discarded. All right, it's being discarded in the cold reservoir, and that is represented by this arrow. So that is the schematic diagram that explains the process of uh, how the second law of thermodynamics is applied, no? In the operation of any heat engine such as a gasoline engine. Right, so going back now to our solution to this problem. First, to find the work done or the mechanical work, okay, using the formula W is equal to QH minus QC. So we just substitute the amount of heat input and the amount of heat discarded. Okay, 550 joule minus 335 joules will give us 215 joules of mechanical energy. And for letter B, we use the formula uh, to determine the value of the temperature of the hot reservoir, the cold reservoir, Tc. Okay, using this formula, the magnitude of Qc over the magnitude of Qh is just equal to Tc over Th, and transposing the formula so that we will have Tc as in one or on one side of the equation. All right, Tc becomes equal to Qc multiplied by Th divided by Qh, substituting, and we will get the value of 378 Kelvin as the cold reservoir temperature. And finally, getting the efficiency, again, we make use of Carnot efficiency formula, 378 Kelvin divided by 620 Kelvin, that is Tc over Th subtracted from 1, and we get 0.39 as our Carnot efficiency, or sometimes called thermal efficiency of the cycle. This is now our last question, another problem solving. Uh, Entropy change in a temperature change as well as during vaporization of water. Okay, so we are asked to compute the change in entropy of 1 kilogram of water at 0 degrees Celsius. All right, that's heated to a temperature of 100 degrees Celsius. That's for letter A. And for letter B, the same amount of water, 1 kilogram, okay, that is made to vaporize without changing the boiling temperature at 100 degrees Celsius. To vaporize, meaning to change its phase from liquid to gas, or uh, converting liquid water, boiling liquid water to steam, okay, at 100 degrees Celsius. So let's begin with letter A. Okay, this process, okay, the process of heating the amount of water from 0 degrees Celsius to a much higher temperature, 100 degrees Celsius, okay, it's like bringing the temperature of water from its freezing point to its boiling point. This kind of process is considered irreversible. All right. So, if the process is irreversible, how do we find the change in entropy? Right. This is the formula for finding the change in entropy of the system. This has been derived using integral calculus. So, we will not discuss that, of course, how this formula came about, but it is simply, okay, equal to, delta S is simply equal to the product of the mass of the given substance, in this case, water, times the specific heat of the substance, and multiplied to what we call the natural log, the natural logarithm of the ratio, okay, of the final temperature, Kelvin temperature, that is, divided by the initial Kelvin temperature. So, when we substitute, the mass is 1 kilogram. Specific heat capacity of water is 4,190 joules per kilogram Kelvin. And we get the natural log of the ratio 373 Kelvin divided by 273 Kelvin. So, with the help of your cycle, you will be able to get this value for delta S, which is positive 1.31 raised to the third power joules per Kelvin. That is our answer to letter A. Now for letter B, uh, converting a given amount of water, okay, to steam without changing the temperature. So this is an isothermal process, all right, where the temperature stays the same. It's considered reversible, whose formula for determining the delta S is simply dividing the amount of heat Q over the Kelvin temperature. But the amount of heat Q used, right, to vaporize makes use of a constant known as the heat of vaporization for water, and that is equal to 2,256 raised to the third power joules per kilogram. So we multiply that by the mass. By the way, the mass multiplied by this heat of vaporization will result to a positive Q. In other words, the system, which is water, has to absorb, right? It has to absorb this amount of heat, okay? And therefore, the sign for our Q must be positive. Then, after multiplying this, we will divide it by 373 Kelvin, which is the temperature equivalent to 100 degrees Celsius. So we get the delta S of the substance or the system, which is water, amounting to positive 6,048 joules per Kelvin. This is the change in entropy, a positive change in entropy. So there we go. We are done. And that will be all for this tutorial. Hope to see you in the future video tutorials. Thank you very much for your indulgence.